Hi everyone. In this short video I'm going to explain you how to draw the Nyquist plot for a system with 3 poles at the origin and the 0 on the left half plane. And then based on the Nyquist plot, I will discuss the stability of the system for different values of k. So one thing that we usually do when drawing the Nyquist plot is to set k equal to 1. As a result, here we will have L of s equal to s plus 2 over s to the power of 3. Then as the next step, usually you need to draw the Nyquist contour, which is indeed in the s plane, where you determine the location for the poles and zeros of the loop transfer function. Here we have 3 poles at the origin, and we have a 0 at -2. Then we need to draw the Nyquist contour for our system. And that contour, the Nyquist contour, should include the whole right half plane, and it shouldn't cross through any 0 or pole for of the loop transfer function. So what we can do here is to have the contour drawn like this. So as you can see here, since the radius for the bigger half circle is infinity, the contour covers the whole right half plane, and in the vicinity of the origin it goes around the poles, so it doesn't pass through the poles, but it goes around the poles. And in this case we have the poles outside of the contour. You should know that another approach would be to go around the poles at the origin and include them into the contour. However, there will be no difference in terms of the final result. So I will take it in this way to exclude the poles from my contour. And now if you pay attention here, there's no poles inside the contour. As a result, we will have p equal to 0. So you know that z is equal to n plus p for the Nyquist plot, where p is the number of open loop poles of the system on the right half plane, n is the number of clockwise encirclements of the point -1, and z is the number of unstable poles of the closed loop system. Now we can start to draw the Nyquist plot. As you can see here, we have indeed 3 segments for the contour. The first segment is here. I will call it segment number 1. The second segment is here, which could be called as segment number 2. The third segment is here, which I will call it segment number 3. And we have also segment number 4 here, which is indeed what we get as the Nyquist plot will be the mirror of the segment 1 with respect to the real axis. However, I will call it just segment 4, and you will see how we draw the Nyquist plot for that segment. Okay, so now we can start to draw the Nyquist plot for the first segment. For segment number 1, we have s equal to j omega, where omega goes from 0 plus until plus infinity. So I assume that here at this point we have omega equal to 0 plus some value just a little bit bigger than 0. So in this case I can write L of s equal to L of j omega, for which we will have j omega plus 2 over j omega to the power of 3. And now for this I can see that first of all I can refer to the body plot of the system. So if you wish, we can draw the body plot for this system, very quickly. We have omega amplitude of L and phase of L. We have two terms. For one term, cross corner frequency is equal to 1 over 2 or 0.5, and for the other term at the denominator, the corner frequency is equal to 1. So I say that here we have omega equal to 1. Here we have omega equal to 0.1, 10, and so on and so forth. In terms of amplitude, we will have for the okay, so let's assume that here we have 20, 40, 60, and minus 60 decibel. For the term at the denominator, we will have 0 dB at omega equal to 1, and for each decade, we will have 60 decibel of change in terms of the amplitude. So this will be what we get roughly, yeah, minus 60 dB per decade. And in terms of phase, we will have minus 3 times minus pi over 2. So if I assume that here we have minus pi over 2, minus 2 pi over 2, and minus 3 pi over 2, we will have this minus 3 pi over 2. For the second term, which is j omega plus 2 here, corner frequency is equal to 2. I assume that it's here. So until that frequency, we will have 0, and afterwards we will have 20 decibel per decade. And in terms of phase, we will have around that frequency, we will have pi over 4. So it's here. 1 decade afterwards, we will have, so somewhere around here, we will have pi over 2, and 1 decade before that, we will have 0. So indeed, this is what we will have for the phase of the 0. And to obtain the overall phase for the body plot of this system, for phase and indeed amplitude, we need to add these to each other, and that's what we will have here. So until omega equal to 1, and indeed until omega equal to 2, we will have minus 60 decibel per decade. And afterwards, because of the effect of the 0, we will have minus 40 dB per decade. And in terms of phase, until this frequency, we will have only minus 3 pi over 2. And afterwards, we will have, after this frequency, we will have minus pi because we have the contribution of the 0. And this will be indeed what we get for the phase of the system. So for low frequencies, we will have minus 3 pi over 2. For high frequencies, we will have minus pi. And around omega equal to 1 or omega equal to 2, indeed, we will have the change of the phase. And then we can use this information in order to plot the Nyquist diagram for our system for the segment number 1. So let's see how we can do it. Here we will have S-plane for drawing our Nyquist plot. So I will start by having a look at L of j omega, which is again j omega plus 2 over j omega to the power of 3. We see that as omega goes towards 0, or we can say omega equal to epsilon, which is indeed 0 plus, in terms of amplitude, we will have infinity. And in terms of phase, we will have minus 3 pi over 2, and that's obvious from here, yeah? Minus 3 pi over 2 for very low frequencies, and 0 in terms of the amplitude. So this means that for omega going towards 0, we will be somewhere around here. But we need to determine in which area are we. Is the phase smaller than minus 3 pi over 2 or bigger than pi over 2, bigger than minus 3 pi over 2? And for this, we can refer to the phase of L of j omega, and it's equal to inverse tangent of omega over 2 minus 3 times pi over 2, and evaluate it at omega equal to epsilon, where epsilon is a very small value. So we will have inverse tangent of epsilon over 2 minus 3 pi over 2. And since epsilon is very small, we can write it in the form of epsilon over 2 minus 3 pi over 2. Or we will have minus 3 pi over 2 plus some epsilon. So this means that we will start our Nyquist plot from this area. So here we have omega equal to 0 plus. Now we can think about amplitude of L and phase of L of j omega as omega goes towards infinity, plus infinity. And we can see it, first of all, here from the body plot. We can see that phase of L is equal to minus pi at omega equal to plus infinity. And in terms of amplitude, we can see it from here again from the amplitude plot as well. Amplitude is equal to 0 or it's equal to minus infinity in terms of decibel. We can also can check it here referring to the phase of L of j omega. So inverse tangent of omega over 2 minus 3 pi over 2. When omega goes towards infinity, we will have minus pi over 2, plus pi over 2, minus 3 pi over 2, or we will have minus pi. And in terms of amplitude, we will have square root of omega squared plus 4 over omega to the power of 3. As omega goes towards infinity, we will have omega over omega to the power of 3, or 1 over omega squared, which is equal to 0. So at omega going towards infinity, we will arrive at the origin with the angle of minus pi. And as you can see here, we see that as omega increases, the phase goes from minus pi over 2, it increases, and at infinity we arrive at minus pi. So the phase part will never go beyond minus pi, or it will not become bigger than minus pi, let's say. As a result, we will have something like this graph for the segment number 1. And there's no need to find the amplitude and phase for any intermediate frequency like omega equal to 1. We don't need it, yeah, or omega equal to 2. But you can do it if you wish. We can now draw the Nyquist plot for segment number 4 as well, because we know that it's the mirror of segment number 1 with respect to the real axis. We will get something like this. So here we have omega equal to plus infinity, and then we have omega equal to minus infinity until omega equal to 0 minus. We can draw the Nyquist plot for the second segment. In the second segment here, we have S equal to RE to J theta, where R goes towards infinity and theta goes from pi over 2 to minus pi over 2 in a clockwise manner. So we will have L of S equal to RE to J theta plus 2 over RE to J theta to the power of 3. And since R goes towards infinity, we can neglect these 2 here. As a result, we will have RE to J theta over RE to J theta to the power of 3, or we will end up with 1 over R squared E to J to theta. And we can rewrite it in the form of 1 over R squared times E2 minus J2 theta. However, since R goes towards infinity, we see that amplitude of L of S is always equal to 0. So the whole second segment will be mapped to this point at the origin. So this is representative of the second segment, and this is for the segment number 4. So now maybe the most important part, the most difficult part of drawing the Nyquist plot is for segment number 3 here. in segment number 3, we start from omega equal to 0 minus with a counterclockwise movement. We arrive at omega equal to 0 plus, and we can represent S with re2j theta here, where r goes towards 0 and theta goes from minus pi over 2 towards pi over 2 in a counterclockwise manner, or let's say crossing from 0. So for that segment, we can write again S equal to re2j theta, where r goes towards 0, and theta from minus pi over 2 to pi over 2 in a counterclockwise way. Therefore, L of S will be equal to re2j theta plus 2 over re2j theta to the power of 3. And since r goes towards 0, we can neglect re2j theta in the numerator compared to the 2, and we get 2 over r to the power of 3 e2j3 theta. Or we will have capital R e2 minus j3 theta, which could be written in the form of r e2j alpha, where r goes towards infinity and alpha is equal to minus 3 times theta. Since r goes towards infinity, this means that we will have a huge semicircles in our Nyquist plot, and since alpha is equal to minus 3 times theta, and the original Nyquist contour here was a small semicircle, which had a counterclockwise movement, our resulting Nyquist plot will be a huge semicircle due to this, and we will have 3 times the semicircle in the clockwise manner, because the original one was counterclockwise. So this means that alpha will, since theta goes from minus pi over 2 to pi over 2 in a counterclockwise way, alpha will go from minus 3 times theta, or 3 pi over 2, to minus 3 pi over 2 in a clockwise way. And one other point is that we will start from omega equal to 0 minus. So the connecting point will be this point, because our Nyquist plot will be a continuous plot. So starting from that point, we will have our Nyquist plot in the form of huge semicircles, which span 3 times pi over 2 angle, and then we will arrive at this connecting point, which is omega equal to 0 plus, or this point here. So, and this will be indeed the direction for our Nyquist plot. So you can see that since we have 3 poles at the origin, and we had a counterclockwise semicircle here, again around the origin, in the corresponding Nyquist plot, we end up by huge semicircles, which span 3 times pi over 2 angle, and they are in the clockwise way. It's opposite of the counterclockwise semicircle that we had in the Nyquist contour. Yeah. Okay, so even without referring to all these formulas that we went through here, by looking at the number of poles at the origin and the direction of the semicircle at the origin, around the origin, you could decide about the number of semicircles that you would have with the radius of infinity for your system. Okay, so this is all for the Nyquist plot. Now we can discuss the stability of the system for different values of k. We have selected k equal to 1 at the beginning. Now we can discuss the stability for different values of k. We take the point minus 1 over k, and we say that if we start to place the minus pi over k at minus infinity until 0, we can count the number of clockwise encirclements of any point in this region. Yeah? If you pick a point, let's say here, now we see that there is somehow one clockwise encirclement here, and one clockwise encirclement here. So we can say that n is equal to 2 for that region. And since we already know p was equal to 0 because we didn't have any pole inside the Nyquist contour. And from here we can reason that z will be equal to p plus n, or z will be equal to 2. So we can say that closed loop system will be unstable with 2 right half plane poles, or 2 unstable poles. For minus 1 over k between 0 and plus infinity, for any point in this region, for any point in that region, we will, let me just erase the encirclements that I had drawn for the system. For any point in this region, we can see that there is only one encirclement. Yeah, the Nyquist plot goes around that point only once. So in this area, n will be equal to 1, and since p is already equal to 0, we will have z equal to 1. And this means that the closed loop system is unstable with one right half plane pole, or one unstable pole. And as a result, we can see that for any value of k, for k in R, the closed loop system is unstable. And you can verify this by referring to the root locus of the same system. Yeah, I think you can do it yourself. It's not that difficult to draw the root locus for this system. Okay, so I think that's all for this video. I hope you have learned how to draw the Nyquist plot, especially when there are some poles in the origin. And then you have learned how to discuss the stability of the closed loop system based on the Nyquist plot that you get for the open loop system. So thank you for watching, and see you in the next video.